Well, hi class. This video is going to help with 11.1, and that's our first derivative and graph. So this whole chapter is going to be kind of like, what does the derivatives, we do first derivative and we actually do second derivative. So that's why we're suddenly calling it a first derivative. And it tells us different stuff about our graphs. So that's where we're headed. This whole chapter is about graphing and derivatives. So let's look at what the notes say here. They say increasing and decreasing. So it's saying for the interval A to B, whatever that is, maybe it's 1 to 10, the derivative is greater than 0 when it's increasing. It's less than 0 for the derivative when it's decreasing. So I'm going to sketch a graph real quick. I just added an extra piece of paper over here. If I have my X, my Y, like I said them backward, I do that a lot. And then we kind of look like this for our graph. So this sort of looks like maybe an X to the third. This would be our top right here. This would be the bottom. If I look at from here all the way up to here, that is increasing on our original function because you are going up to the right. So this is up towards the right because the right is up this way, right? So then from here to here, that's decreasing because you're down to the right. Okay, so this is our right side again. It's going down. Then from here to here is increasing again. So I can look at the original graph, and I can see where something's increasing, decreasing, and so forth. I can also look at the derivative, and it will tell me that same thing. Where is it increasing? Where is it decreasing? Because this section, the derivative will be positive, negative, positive. Okay. The other things we're going to kind of look at as well is that this would be a local maximum. And that this would be a local minimum. So those vertexes on any, parabola, or like this one, like x squared that has 2, you have that point where it crests, or that vertex, that top spot, that can be called our local max or local min. And what you can see as that is it's going to switch from increasing to decreasing at a local max. So increasing to decreasing. A minimum goes decreasing to increasing. So we're going to look at that as well with the derivative idea. Okay, so I'm going to scroll back up. And it goes through what we call the critical values. The critical values are where the derivative equals 0. Excuse me. We also look at any points that we would have a vertical asymptote, like 0 in the denominator, things that we can't have. Those can also be included in what we call a partition number. So they aren't a critical value, but we have to look for those as well. So where the derivative equals 0. So down here, we have what does the first derivative test for local extreme. So this is just what we just said. For local minimum, local max, it's going to change from negative to positive, and then positive to negative. Okay, my screen just went dark in the middle of my recording. Did I click something? I'm on my iPad, so I don't understand where I would have clicked. Okay. Guess you could fast forward the teacher going, why isn't it that one? Is it control? No, it's function. I don't know. Okay, it's back a little bit. It's still a little bit dark. I'm sure it's fine. Okay, then let's look at a problem and see what we're actually doing. So what we're going to do is we're going to start by finding the derivative. So if we look at this, the derivative, this one's a pretty basic derivative. So 3 times 3 is 9, x squared minus 81. So we went from an x to the third to an x squared. We went down 1 power. Then from there, we're going to say, okay, the critical value of the function. So remember, the critical value is where the derivative equals 0. So I'm going to do it down here, part B, and that is where 9x squared minus 81, where does this equal 0? These are the values where we could switch from increasing to decreasing. So we have to look at those. So we'll add the 81 over and we get 9x squared equals 81. Divide by 9 and we get 9. So x squared equals 9. So I get two values, positive and negative 3, when I take the square root. Okay. And then when it talks about the partition numbers for the first derivative, what it's referring to is what numbers. Basically, do you have any spots where you would have 0 in the denominator that also need to be considered with this 3 and negative 3 for places where you could possibly going from decreasing to increasing? This one, we don't have an x in the denominator. Our domain is all reals. We don't have like a number that makes undefined right here, okay? So our critical values are just the 3 and negative 3. Okay, and then this was just that picture I drew. All right, so this one's asking the same thing, critical values and so forth. So let's go through this. Start with the derivative. The derivative of this is, I might have to have some more room. I'm going to do it down here. The derivative of this is a quotient rule, right? So we start with the original bottom, which is x plus 3, and then we times that by the derivative of the top. What is the derivative of 21? 0. Minus the original top, which is 21, times the derivative of the bottom, which is just 1. So I didn't write out t equals b equals because the derivatives were pretty easy. You could always do that the way I showed when we went through that section. And then x plus 3 squared. Oops, why did I write a 4? Really wanted that number to be a 4, I guess. Squared, like this. So this is the derivative. Well, 0 times anything up here is 0, and then minus 21. So our final one will be negative 21 over x plus 3 squared. Now this is our derivative. Okay, so what are we going to do from here for our derivative? We're going to... Sorry, I was looking to see if I had. So from here, we can look at, okay, so that's our derivative, our critical values. I was trying to find my key, not a big deal, not that I really need it, but the critical values are where negative 21 over x plus 3 squared, where does that equal 0? So if I look at this for critical values, well, I can times this denominator up to the 0 and get 0. So really I have negative 21 equals 0. I can't have that. There's no solution. So what that means is there's no critical values. Now, that doesn't mean that there's necessarily no points where I go from negative or from, decreasing to increasing that I have to look at. I still have this partition number and for part C, and that does come up with this one because we do have a place where the denominator equals 0. So think about your domain, right? We have to look about under a square root, can't have a negative. You have to look at anything in the denominator with an x. That's it, right? I think those are the only ones. So for C, can you see that you cannot have a negative 3? So I have a partition number at x equals negative 3. Okay, and that's it. All right, so then from here, we're going to go a little further. We're going to say, okay, we now know critical values are where the derivative equals 0, and those are just those places where I can go from increasing to decreasing or positive to negative on the derivative. So let's look at kind of the whole kit and caboodle for these. So we can find the critical values, find the partition numbers if we have one. And then from there, then we can decide increasing, decreasing, and we can also decide if it does have a local extrema, that's a local min or a local max. So let's start from the beginning on this one. So we start with the derivative. So that's going to be 10x plus 20. Okay. Then I have to find the critical values. And that's where the derivative equals 0. So 10x plus 20, where does that equal 0? So I would minus the 20 over, divide by the 10, and I get -2. So on this one, I have a critical value at -2. Do I have any partition numbers? That's going to be, do I have an x in the denominator? Nope. So what I'm going to do now is called a sign chart for increasing, decreasing. Now you did do these in 1400 as well, but of course we're going to add the derivative piece to it. But basically we're going to make a sign chart, and we're going to put all critical values and partition numbers on our sign chart. And I only have the -2. From here, what I'm going to look at is where is the derivative positive and where's the derivative negative. So I'm going to do a little chart here. And the y, and this is of the derivative. So this is of the 10x plus 20. And we'll put a number in less than 2, so, or less than -2, excuse me, maybe -3. And we'll go 10 times -3 plus 20. So 10 times -3 is -30, plus 20 is -10. So I got out a negative number over here. -2 is a 0 because it is where it's a critical value. Derivative equals 0. This sign chart's of the derivative. So it's -0. Then I put in a value above -2, like maybe 0. You could do -1, whatever you want. 10 times 0 is 0, plus 20 is 20. So this one came out positive. Okay, so with this one, we went from negative to positive, and we had that critical value at -2. So we do switch from negative to positive. And remember, negative is where the original function is decreasing. So the original function is decreasing here. And the original function is increasing here. Because our derivative tells us stuff about the original. That's what it does. So we don't want to talk, we have to always talk about the original function. Okay, so we have the decreasing, increasing, and then we went from a negative. So we were down and then back up. So if you think about that one, because you were decreasing and then you switch to increasing, it's a local min. It's a minimum value. So what is our solution? You have to give the intervals in which the function is increasing, intervals in which the function is decreasing, and the local extreme. So for part A, I need where it's increasing. It's increasing from -2 to infinity. Okay, so it's increasing from -2 to infinity. For part B, where is it decreasing? from negative infinity to the negative 2. And what is the local extreme? It's a local min at x equals negative 2. So this is a sign chart, and this is where everything comes together. Okay, let's do another one. Maybe one that's not so easy. Still easy. Still easy. Doesn't it give us a little bit harder ones? Meh. We'll just do one more little bit easier one. Problem 5, and then I'll just change the others, which is what I have on my notes. I have on my notes, need more examples. And then last year I had like posted extra videos because I was like, you're gonna want to see a couple more. Okay, so look at this one. And now I could just say, where is this function increasing, decreasing? And I want you to use derivatives to do it, right? Because we could just graph it and see where it's increasing and decreasing, but I want derivatives. And then I want you to list any local extreme. So we start with derivative. Okay, so 4 times 3 is 12, x to the third, plus 4 times 3 is 12x squared. And that's all we have on that one. Okay, then from here, we're going to find our critical values. So where does the derivative equal 0? So 12x to the third plus 12x squared. Where does that equal 0? Well, we can take out an x squared, and we would be left with 12x plus, oh, I should take out a 12. I'm going to do that again. I want to take that out as a 12x squared. Take out the whole GCF, the numbers as well. So I'd be left with x plus 1 equals 0. Okay, so when I take out an x squared, x to the third, just an x, that gives me the solution of 0. And then we also have the solution of negative 1 from the parenthesis. So we have two critical values at 0 and negative 1. Do we have a partition number that we need to include? No, we don't have an x in the denominator. So we don't have an additional number to add to our number line. Okay, so our number line is only going to have 0 and negative 1. Now, if I was to have something in the denominator, it would just be another number on that number line. Okay, then again, we're going to look at where is the derivative positive and negative. So I'm just going to do a little chart here and see what I get out. So I'm looking at the 12x to the third plus 12x squared. And we'll put in something less than negative 1, like maybe negative 2. And then we put that in, I don't know, this has got too high of powers for me. So 12 times negative 2 to the third plus 12 times negative 2 to the second. And I got negative 48. Okay, so I got a negative here. And this is a 0, this is a 0, and this is all of the first derivative. Okay, we have second derivative coming in the next section. So we do label our sign charts that they are of the first derivative. Okay, something between negative 1 and 0, I don't know, negative 0.5. So again, I'm going to go secondhand enter and bring in my whole same function I did before. And this time I'm going to change my negative 2 to 0.5. And I have to use the insert key, but that's okay. Negative point insert 5. We just have the 2 spots. Yeah, I got positive 1.5. So I didn't show the work here, but it's really just 12 times negative 0.5 to the third plus 12 times negative 0.5 squared, like that. So I got a positive here, okay? And the last section would be something above 0, so maybe a 1. So 12 times 1 plus 12 times 1 would be a positive 24. So we look at that one, and I can see it goes negative, positive, positive. Okay, so I'm gonna have this one graphed. I'm gonna show you the graph. So 3, this one's a little bit different. Oops. Um, 3x to the third. Okay, so this one, our original function is looking like this. So can you see why we have that? You know, it's positive, positive, but it has a little hiccup there. That's why we have that other critical value with it. So, because it's a fourth power, so it still like goes up and then up again, but it kind of looks like that. So when we go to answer, where is it increasing? Where is it decreasing? We would have increasing, and we say from -1 to 0, and also from 0 to infinity. We say both of those, okay? Decreasing, we would then say from -infinity to that -1. And we could see that on our graph. We are decreasing down, and then we're increasing, and then we have a little hiccup, and then we are continuing to increase. So we can kind of see that from the graph there. Okay, so critical values are here if it asks, and then increasing, decreasing. Oh, does it have a local minimum or a local maximum? Well, we just looked at the picture, so I could see it's low. So if it goes from negative up here, right, negative, negative to positive, then it's going down and then back up. So it has to be a local minimum, and it has to be at x equals -1, because that's where we switch from negative to positive. At the 0, we don't have a local min or max because it doesn't switch from negative to positive. And if I blew this up a little and I touched that spot, I could see it is a -1 at that spot. This spot here, I can see is at a 0, right? And that's where we know that that's at 0, but it's still increasing, increasing. So it is not a local min or max. Okay. Did you know you can't take the derivative of like a spot that's like a V? So our absolute value right at that vertex when it comes in, if I cannot draw like a straight line, like a tangent line at that spot, I can't take the derivative at that spot. I don't know if that's taught somewhere in our book or if it's kind of skipped because we don't look at the graphs enough. But I think you had a couple questions on whether you could take a derivative at a spot, and just know it can't come to a V. You can't take the derivative at an asymptote. I'm lost. I think that's the only ones I can think of off the top of my head. Okay, so I am going to change problem 6. Way too easy. Let's change this function to x minus 3 times e to the -7x. Okay, we're still doing the same thing, increasing, decreasing. We could sketch the graph, but I also want local min or max. Okay, do we have that local min or max? So same thing we've been doing. We haven't really sketched the graph until the last one. We could sketch the graph just using technology to see what it looks like. And again, what are we graphing? Original function. All the information we find is about the original function. So problem 6 has a function times a function. So what do we have to use to find the derivative? We have to use the product rule. Okay, so remember the product rule says first times the derivative of the second plus the second times the derivative of the first. So if we think this through, the first function is x minus 3. What's the derivative of f minus x minus 3? Just 1, right? Because the 3 drops off. We just have a 1 in front of the x. Okay, the second part is e to the negative 7x. Okay, everyone's like, e to the x is e to the x, but this isn't e to the x. It's e to the negative 7x. So you have a chain rule inside of this one. So the derivative of this is e to the negative 7x, keeping it the same because the derivative of e to the x is e to the x, times the derivative of the inside, which is the negative 7. So we have to include that negative 7, which is the derivative of the top. That's the part people miss, okay? And so we could rewrite that just as negative 7 e to the negative 7x, like that. Okay, let's put the derivative all together for ourselves. The derivative is now going to be first x minus 3 times the derivative of the second, which is ugly, negative 7 e to the negative 7x. Okay, and we're going to add that to original second times the derivative of the first, which was just 1. Okay, simplify this thing. Well, what I want, well, I mean, maybe I will just show simplifying it. So I'm going to times this through the parenthesis. Okay, so negative 7 e to the negative 7x times x is negative 7 e to the negative 7x times x. Okay, minus, well, a negative times a negative is a positive. So negative 3 times negative 7 is positive 21. And then this would be e to the negative 7x. Okay, and then the other one is just 1 times that is plus e to the negative 7x. That is what we call an ugly derivative. So to find the critical values in the partition numbers, we say, well, where does this thing equal 0, right? And this is to find the critical values. Will we have a partition number? No, we don't have, we can't have negatives in our, we won't get a negative answer from an E. I don't, but yeah, no, we don't have anything too tricky. Okay, but this part is tricky. So I want to factor out that E to the negative 7x, and that will make this thing look a lot easier. Okay, so I'm going to factor it out. We're still equal 0. E to the negative 7x. So anytime you have an E, factor it out because it can't equal 0. So that's where we're going. So this first one, I'd be left with negative 7 and the x, right? Negative 7 and the x plus 21 plus 1. Okay, so then that ends up being a 22. So really we have e to the negative 7x and then negative 7x plus 22. All right, where does each factor equal 0? Well, 0 equals e to the negative 7x has no solution. So that part we can kind of ignore. So if you have an e, you factor it out, and it cannot be a critical value. So we look at negative 7x plus 22. Where does that equal 0? Minus the 22 over. Divide by negative 7. And I get 22 over 7. So our critical value is at 22/7. All right, so then we go to our sign chart, and the only value we have is 22/7, and which is about 3.14. I only know that because in one of the books I taught from, it estimated pi as 22/7. I don't know why. So there we go. And then we look at values below and above for the derivative, right? These are all the derivative. This is a 0. You could put not defined if it happens to be a non-defined spot, but this one's a 0. We haven't had one of those yet. Okay, then from here, I have to put in a value lower than 3, so maybe 0. And we have to go all the way back up to our derivative, maybe in the simplified form here. If I put in 0, this would give me 1, because anything to the e to the 0 is 1, right? Anything to the 0 is 1. And then 0 times this, so I get a positive. I don't really care what the value is. I care if it's positive or negative. So that's got to be increasing. Something above 3-ish would be 4. So maybe I go up here and I put a 4 here and a 4 here. I'm going to have to use my calculator. So I'm going to put in my calculator e to the -7 times 4. And then parenthesis -7 times 4 plus 22. I got an ugly negative. Don't really care what the number is. It was like an ugly decimal. I just care that it's negative. So what's my final answer? I am increasing from -infinity to 22/7. I'm decreasing from 0, not 0. I just was looking at the 0, the 22/7 to infinity. Does it have a local min or a local max? Does it switch from positive to negative? Yes, but this time it's going positive, so we're going up and then back down. So this is a local max at x equals 22/7. Okay, is there anything else? I thought we had added, oh, just what does the graph look like? Let's show that graph. Maybe I will go this way, then it's a little bit clearer for you. Okay, so let's graph this. I'll show it in Desmos. So our original function was x minus 3 e. You have to go to the ABC e back to the power of -7x equals 0 or equals y or whatever. Okay, so it'll show it there. So what was our critical value? Was at 22/7. So where does it start to, it'll show it usually. Where does it start to? It might be over, yeah, because it was at 22/7. I don't see where there it is, 3.140. Ew, that's hard to tell. That's hard to tell where it's switching from increasing to decreasing from the way it graphs on here. Yeah. So that's what that one is kind of looking like. So it's going up. What did we say? We said it's going, yeah, increasing and then decreasing. I really can't tell that's decreasing. And I typed it in right? Yeah. I can't tell that's decreasing. Maybe that's just because it's getting really close. I don't know if we could tell from here. I'm not going to worry about it too much, but maybe we could tell if we zoom in here. No, I still can't tell that it's going up and then back down. Maybe by the values, if we had a chart. Yeah, it's starting to go, I don't know. It just rounds it to 0. I'm just going to go with the math. It's just kind of an ugly graph to show you on that one. That's probably why when I make it up, it probably would have never made you graph it, but that's kind of what the graph looks like. Alrighty, so I think I I need to do at least one more, but I think I have a video of it. So I'm going to stop this video here and I will just include like part 1 and part 2 for you.